The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone to the second webinar in the GO0DMAN webinar series. My name is Christopher Gadowski and I work for BOC in Austria. Today's presenter will be Paolo Chiariotti from the Marche Polytechnic University, and he will give an orientation regarding smart inspection tools in the scope of the GO0DMAN project. Before we get started, let's touch on a few organizational details. So this webinar is planned to take about 45 minutes, and we'll start with a couple of guidelines. The subsequent content section is where Paolo will give us the orientation regarding the smart inspection tools in all three use case organizations of the GO0DMAN project, and we will finish with a fade out where any arisen questions may be answered directly. One important note for this webinar is that all attendees are muted. Regarding all questions, please feel free to use the chat window located in the bottom right-hand corner of your GoToMeeting panel, and we shall take a look at them during the fade out of the webinar. Another important point is that if you would like to rewatch this webinar on a later date, this webinar is being recorded and will be made available online for on-demand viewing. All right. Those were the organizational details, and now I'd like to hand the floor over to Paolo Chiariotti to give us the Smart Inspection Tools presentation.
Okay. Thank you, Christopher. Good afternoon, everyone. So, my name is Paolo Chiariotti. I'm a researcher at UPM, University Polytechnic of Marche. I'm here today to talk to you about our development in terms of smart inspection tool within the GO0DMAN project. As you may know, in modern digital factories, performing inline quality control on 100% of production is a key strategy to target a zero-defect production. This is particularly relevant in multi-stage production systems. In this case, real-time and early identification of deviations and trend performed both at single-stage level allow to prevent the generation of defects and their propagation to downstream processes. And in this case, this enabled the entire manufacturing system to perform early detection of process deviation and self-adaptation to varying conditions. In this context, it becomes clear that a zero-defect strategy requires reliable information to support any decision. Of course, reliable information requires measured data from the process and the product. But in a real production scenario, availability of data does not by itself guarantee an effective information build-up. In particular, measurement uncertainty must be known, kept under control, and adequately managed, so to keep the confidence level on measured data at the required level. Within this context, the GO0DMAN project is implementing in a multi-stage manufacturing production line a distributed system architecture built on a joint use of agent-based cyber-physical system and smart inline quality control system. The GO0DMAN architecture has been designed to demonstrate that cyber-physical systems are the key technology to reach the zero-defect target aimed by the manufacturing field. We can identify three fundamental layers: the bottom layer, which involves the production line and the quality control system, the control layer, ruled by the multi-agent system structure, and the top layer, representing the decision layer grounding on data analytics and knowledge management. This talk wants to provide you with an overview of the bottom layer, aiming to show that quality control system exhibiting smart behaviors such as continuous adaptation of the sensing parameters to the variable product process parameters and characteristics, and to environmental changes really represent a local cyber-physical system which is fundamental to enable a zero-defect strategy. As you may know from the previous webinars, we have three industrial end users working within the GO0DMAN project: the Volkswagen end user, the Nini end user, and the Electrolux professional end user. In terms of smart inspection tool, smart quality control system, we have to develop different solutions for the different target that were targeted by the three end users. For the Volkswagen use case, the target was to develop a portable device to measure gap and flash on tailgate, rear glass, chrome components, and rear headlights of the T-Roc model in the assembly line. This is to reduce operator intervention, which means reworking. The target uncertainty for this device is 0.5 millimeters. For the Zanini use case, we actually had to develop two devices. The first one is a contactless inspection tool for measuring the geometrical features of boards in order to reduce compensation in the owning process. Here again, the target uncertainty is less than 5 microns. The second device was aimed at developing an automated inspection tool to identify the presence and location of birds. When we mean birds internal component, we are referring to very small parts around 1 millimeters long and 0.5 to 0.1 millimeters thick internal components to reduce reworking. The Electrolux use case was addressing two different issues. The first one was related to the development of a device to highlight present location of leaks on the oven front door assembly to reduce heating inefficiency, and to measure the gap and flash on the oven front door frame assembly for aesthetical and functional purposes. In this case, also the target uncertainty is less than 0.5 millimeters. But at the same time, there were other requirements from the Electrolux professional use case, which means developing a device to identify noisy faulty fans in the oven assembly. This was targeted by Locioni. And the development of a device to identify wrongly assembled components in the oven. This again was assembled by Locioni. All these topics were addressed by task 3.1, which is the task of the GO0DMAN project addressing the line quality control system. The introduction of smart features to this device, which means self-adaptive behavior, self-diagnosis and self-calibration capabilities, and the modularity of tests, plug-in, plug-out, were addressed specifically in tasks 3.2, 3.3, and 3.4. Everything together builds up the work package 3 of the GO0DMAN project, which is the one addressing the smart online inspection tools. Let's get started from the Volkswagen use case. So, as I said, the target here was to measure on very different surfaces, which means tailgate, so metal parts, rear glass, chromed components, and rear headlights, so plastic parts. Again, the requirement from the Volkswagen end user was to ensure the device portability. As you can see from the picture, the current solution involves filler gauge, but at the same time, this solution cannot allow to store data in an automated way. So what we propose to develop within GO0DMAN is the development of a handheld laser scanner, which is based on optical triangulation. But the particular aspect of this device is that it is portable, so the man is still in the loop. This implies a series of consequences that has to be taken into account. For instance, the operator's safety, a balance of the uncertainty, because of course, if the operator is holding the device, there is much higher difficulties in reaching a target uncertainty less than 0.5 millimeters. And of course, also ergonomicity has to be taken into account. What we came up with a cell phone-based optical triangulation devices. This device allows to perform an automated measurement by recognizing in an automated way the area where the system is measuring. This is done through a deep learning approach. The laser can also conditionally switch on and off, and the exposure time can be adjusted based on the target recognition, so based on the area recognized by the system. There is a possibility to work in a hybrid mode, which means contact or contactless operating mode. In this case, the device works up to a target to device distance of 40 millimeters. By optimizing the laser wavelength, we managed to measure on very different materials, which means metal, plastic, chromed parts, and glass. There is also a possibility by exploiting the cell phone to provide the operator with a feedback with respect to the measurement accuracy. The data transmission takes place by using OPC-UA protocol, and it takes place by Wi-Fi. So there are a series of hardware solution together with some software solution that makes it possible to reach these, to fulfill all the requirements provided by the Volkswagen use case. Basically, we develop a smart cover for the cell phone, in which we embedded a laser source, which is working in the 405 nanometers wavelength. So basically, it's a violet laser. We are embedding white LEDs on this cover in order to make it possible to recognize the area where the operator is measuring on and where the operator is pointing the device. Of course, we have the camera because we have developed that optical triangulation system. And there is also a time-of-flight laser ranging module working in the 940 nanometers range in order to detect the target to device distance. Everything is managed by a Raspberry Pi Zero board, which manage all the sensors that have been embedded within the cell phone. And the cell phone itself is used for performing calculation and for ensuring interaction with the line. So we are exploiting, for instance, the cell phone camera in order to scan the barcode of the car that is actually the one which is measured by the operator. Of course, this has been a long journey towards the definition of this solution and implementation of this solution. So basically, we started with a cable solution where ergonomicity was not that important. We were more interested in assessing the accuracy of the measurement. And then, since then, we started working on improving the ergonomicity, which means moving from a cable solution to a wireless solution, trying to reduce dimension of the system as well, and so on and so forth. So basically, we moved from calculation performed to a remote PC to calculations performed on board. And the final solution performs every calculation, as I said, directly on the cell phone. In terms of middleware, the system is based on a web service which manage the hardware, so cameras, distance sensor, and etc., and some software resources, for instance, the automated recognition of the measurement area. It is possible to synchronize the configuration of different devices by a REST service, and also it is possible to storage data measured by using an SQL database engine locally or in a global way. As I said, communication is based on an OPC-UA protocol, and it's quite easy to set up the device for a robotized application, since everything is prepared to be used in a robotized application. We got luck because the system was patented. We filed a patent in March 2018, and we got a positive patent report in July of the same year. So we are now in the way of the technology transfer. So we are trying to transfer this technology to an industrial end user in order to implement in an industrial way this device. I just want to show you a short video reproducing the measurement capabilities of the system. So the device is pointed towards the part, the measurement is performed, and then a feedback is provided to the operator. The lady who was showing in the video is actually Elisa Minetti, who's the one who developed the tool together with the UniVPM team. For the Zanini use case, as I said, we had to face two targets. So development of a contactless inspection tool for measuring the geometrical features of boards, and a tool to automatically identify the presence and location of bars. All these tools are aiming to reduce reworking of the parts. Let's get started from the first one. So basically, the current solution for this task foresee the use of a contact probe. There are a number of issues in using a contact probe for fulfilling this task. Different sample diameters need different probes. There is not possibility to measure transversal location, and the operator is still in the loop. So what we proposed within the GO0DMAN project is to go contactless, and most of all, to use a confocal chromatic technology to perform the measurement. There are several advantages in doing that. The possibility for sure to automate the inspection, the possibility to work at variable spatial sampling, so in this way ensuring the modularity of test, and the possibility to measure the transversal locations. This is the conceptual device that we developed. So we have 4 stages ensuring vertical movement, a rotational movement, and a planar movement on the XY stages in order to ensure centering of the probe with respect to the part. On the right side of the slide, you can see the final installation of the system. However, there have been some issues to face. Mainly, 3 issues were identified. How can we be sure that the sensor is centered within the sample? We also know that confocal chromatic sensors are influenced by temperature, because temperature influences the refractive index of the sensor optics. So how can we ensure reliable data? And how can we manage a sensor that is primarily designed for differential measurements? So basically, a sensor that is designed to assess difference between different distances between different targets. So we faced this issue, and we provided these smart features to the devices. So basically, a self-centering capabilities, temperature self-compensation capabilities, and self-calibration capability. Let's see everything from the start. Concerning the self-centering, we came up with a strategy to ensure that the sensor is always centered within the part. Basically, we perform a measurement on the 4 different angles with respect to the start position, and then we check the distance recorded on each angle by the probe and compare it with the reference target in order to be sure that distances measured at opposite angles are within a certain threshold. In this way, we can perform an assessment of the centering position of the sensor with respect to the part. For what the temperature self-compensation is concerned, we perform dedicated tests by placing, for instance, the sensor in a temperature test chamber in order to come up with a sensor temperature distance characterization law that could allow us to implement a compensation for temperature variation. Of course, this means we added a temperature sensing device on the final system in order to have information about the actual temperature of the system during the measurement. For what the self-calibration is concerned, we came up with a strategy to perform the self-calibration of the whole system, which is based on a first check on the temporal compensation capability of the system. So we are checking if the temporal compensation capability of the system is working properly. If this is working properly, we go towards a self-centering check. For performing the self-centering check, we are using calibrated rings. If everything's okay, the system is fine, and then it can be used for performing the measurement. Otherwise, it has to be sent to a maintain. It has to be undergo a maintenance operation. This video wants to provide you with a short hint and the working principle of the system. So the part is gripped by an automated way by a gripping system. The sensor is put towards the part to be inspected, and the diameter measurement starts. So the sensor rotates within the part. Everything is contactless, so there's no problem if there is an increment of internal diameter, so we can work on different parts with respect to a single cylinder. Also, the length measurement is performed. Data can also be visualized on the HMI of the device. This is the final installation we had in Zannini, Poland. Final integration is going to take place in about 1 week from now. For what is related to the development of the automated inspection tool for identifying the presence and the location of bars, when we talk about bars, we are talking about this small air in this part, which are about 1 millimeter long and whose thickness ranges from 0.05 millimeters to 0.1 millimeters. So we are really talking about tiny parts of metal components. Why it is important to locate presence of parts? Because this avoids reworking. The current solution is based on a visual inspection performed by an operator. What we proposed is to use machine vision to accomplish this task. We started with boroscopic vision. We set different optical setup by using 45 angled mirror or using a conical mirror, but actually we got unsatisfactory result. So we start thinking together with Zannini, what can we learn from the operator performing the inspection? Okay, we can learn that the sample should be somehow observed from the outside, because that's what the operator is doing. And at the same time, the sample should be rotating during the inspection, because that's something that the operator is doing, is changing his point of view in order to inspect in a more proper way the part to locate the presence of bars. So we came up with this preliminary solution, trying to take an image snapshot while the sample is rotating. Why it is important is this solution? Because there is the possibility to detect the bars on thick samples. If you are rotating, you can really locate bars on the front and on the back side of the holes, and at the same time, multiple holes can be inspected in a simultaneous way. These are also some smart self-adaptive features that characterize this system. And we came up with 3 different actors that put together really allowed us to fulfill the task we were asked to solve. We developed a sample gripping system which is capable of gripping and rotating the part which is gripped within the grippers. We developed an internal radial light source and, of course, a buzz detecting algorithm. This is the preliminary concept. So as you can see in this slide, we have a driving motor, which is numbered with 1. The grippers, labeled with 2. A centering driving cone, which is the one placed on the motor side, and a centering slave cone, which is the one on the opposite side, and 2 internal light stick insertions. They are on board, so basically it is possible to grip the part, insert automatically the light stick within the part, and rotate the sample that is gripped by the system. Of course, since the GO0DMAN project foresee some months of continuous working operation at the end user premises, it was important also to ensure reliability of the system and sufficient endurance of the system. That's why we moved from let's say a laboratory prototype to a more industrial grade device, which is based on an industrial driving motor, which uses slip rings to power light sticks, which uses industrial LED controllers. And we also developed some smart, let's say, engineering in order to make it possible for the light stick to be retractile, this to prevent damages during the gripping phase. So the light stick can be retractile and we can ensure that nothing bad is going to happen to the light stick during the gripping phase. This is again a short video that aims at providing you with an indication on how the system is working. The part is gripped and the internal light stick lights up. There is a visual feedback to the operator who knows if the check has went in the proper way, so if bars have been detected or not, and then the part is released. The good thing of this implementation is that the implementation itself can be twofold. So we can have a robot-assisted implementation in order to perform a pick, place, and inspect operation, or it can be a standalone implementation, which is the one we implemented in the GO0DMAN project. Again, we patented this solution. We, as University Polytechnic of Marche, are co-owner of the patent together with Zanini, and the patent itself was acquired by Zanini in March 2019, so just last month. For what the Electrolux professional use case is concerned, here we split the effort in developing the system with Locioni. For what the development of device to a light presence location of leaks and the assessment of gap and flash on the oven front door frame assembly, we decided to merge the two different solutions in a single device. So basically what we did is we added a further capability to the tools we developed, the tool we developed for the Volkswagen use case, arranging everything in a different layout. In this case, we are going towards a separate stethoscope-like sensing tool. We embedded in this device an ultrasound probe, which is capable to detect leaks once you put an ultrasound emitter inside the oven cavity. So basically, by recording the ultrasound signal by the device, if the ultrasound signal is above a certain threshold, then we are sure that we have found a leak. At the same time, the gap and flash inspection module really resembles what we developed for the Volkswagen use case. So everything is embedded in a single sensor, and the operator feedback takes place on a PDA or on a cell phone. Again, information is provided to the resource agent using OPC UA communication protocol and using Wi-Fi connection. For what the identification faulty fans is concerned, Locioni developed a vibrational test station. Why it is important to identify noisy or faulty fans? In order to reduce this vibration of the whole system, to reduce the acoustic noise, and to detect unbalancing error of wrong assembly of the whole assembly. This is the solution that is going to be integrated within Electrolux Professional production line. It has an HMI touch screen. Here you have a lookup on the accelerometer and a current probe, because these information are merged somehow to be sure that the system is working in the proper condition. And then we have a processing unit, an acquisition board, and other electrical components embedded in an electric cabinet. A triaxial accelerometer measuring a radial axial and tangential acceleration is used in this case. The system has been embedded with some self-adaptive behavior. The first one is related to the possibility to guarantee that the system is able to know whether the motor is running at the proper speed. So this self-adaptive behavior that the vibrational test station is embedded with is to guarantee stability and repeatability of the analysis. So basically, the software checks if a steady state and the set RPM values are reached. If not, a feedback is provided to the operator. The system is also capable of performing a self-diagnosis. In this case, vibration data analysis are used to early diagnose a possible wrong tool mounting and to increase the confidence level of the sensor output. There is a number of features extracted, 16 for each axis, which means a total of 48 features that are extracted from the vibrational signal. If those features that are above a certain threshold, the features are ranked based on Bhattacharya distance. If the features that are above a certain threshold are selected and then used for training a supervector machine algorithm, and the algorithm parameters are used to classify a correctly mounted device with respect to a wrongly mounted device. It is possible to perform sensor calibration with this station, and in particular, the user is guided by a wizard to perform sensor calibration. In this case, a handheld shaker, which is commonly used to perform in-field accelerometer calibration, and a software with a wizard procedure are used to perform this self-calibration. An indication is provided in order to increase or decrease the torque for ensuring the accelerometer assembly on the motor clamp is performed always with the same torque, and to be sure that it has to be increased, the torque has to be increased or decreased with respect to the preliminary mounting of the system. Intelligence is provided to the whole devices. In this case, several faulty conditions have been simulated by Lucioni, as for instance, oven fan unbalance, or cable tie rubbing on cooling fan on the motor side, or loose screws. And if you see the confusion matrix that comes up looking at the possibility to classify these different faulty conditions, the confusion matrix is really good, because everything is classified in the proper way with just some very few cross misclassification of the systems. It is also possible to test the function modularity of the test. Indeed, the system makes it possible to activate or deactivate the different checks according to the information received from the corresponding resource agent, which is associated to that particular system. For what the development of the device to identify wrongly assembled components in the oven is concerned, Lucioni decided to go towards the use of a smart camera automated inspection. They use a Connect Inside 2000 camera, a PC, which is using a FTP server and OPC-UA server. And the bottom of the oven is observed from the smart camera at a target to camera distance of 80 centimeters. In this way, they are able to perform an automatic check whether the assembly is properly performed or not. In this case, some self-adaptive behavior have been embedded within the final solution, as for example, the use of a smart camera auto exposure. So the exposure time is automatically adjusted to compensate for different lighting conditions, continuously or in single shot mode. And they are also performing white balance operation in order to be sure that the proper color images are restored on the recorded images. So for more details on whatever I've been talking about today, please visit the GO0DMAN project website and use the innovation shop in order to get more details. I just want to thank all the team here at UniUPM, Professor Nicola Pavone, Professor Paolo Castellini, Elisa Minetti, and Matteo Fitti, who are two PhD fellows who have been working in the Volkswagen and Electrolux use case and Zanini use case, respectively, and Mr. Luca Violini for all the technical support in terms of informatics stuff. Thank you very much for listening.
All right. Thank you very much, Paolo, for that interesting orientation regarding smart inspection tools. And let's take a look now to see if participants have left any questions in the chat. Okay, it looks like one attendee was not able to see the first video, but I was able to see that video, so that means that it was recorded and it will be available on YouTube when we upload this webinar. Apart from that, I don't see any questions. That means people are still taking in this information. I want to thank you again, Paolo, for your presentation. And to all of our attendees, thank you for being here. Regarding your questions, just as Paolo said, check out the GO0DMAN homepage and the Innovation Shop, and we're happy to answer any questions and support you. This concludes today's webinar. Thanks for your attention, and we wish you a pleasant afternoon.